Hello friends, I welcome you all to Doubt Forum. In this video, we will be learning about the variation in acceleration due to gravity, which is represented by a letter small g. And as we all know that the value of small g is not constant everywhere, its value on the surface of Earth is different from the value at a height from the surface of Earth. And not only this, the value of small g also changes as we move inside the Earth. So its value keeps changing as we move from the center of Earth to its surface and as we also travel above the surface. So the value keeps changing. So here we have to find out that why this variation takes place and what are the factors which determine the variation. So these all things we will be learning in this video. So before we start, let's read out the question first. The question is starting from the center of Earth, having radius r, the variation of g, that is acceleration due to gravity, is shown by, and these four graphs are given. So these four graphs are showing the variation in acceleration due to gravity as we are moving from the center of Earth and moving away. So to understand the variation in g better, we need to understand the Newton's second law first. From the Newton's second law, if there is an object, suppose this is an object, the mass of this object is m, we are assuming it that the mass is m, and if we apply a force, suppose the magnitude of force is F, so due to the application of this force F, this object will start accelerating in the direction of force. The magnitude of acceleration, which is represented by letter A, this will be equal to the force applied on this object. And also remember that the force which I am talking about here is the net force. If there are more than one forces acting on this object, we have to find out the net force first. So the acceleration of this object would be equal to the net force which is acting on this object divided by the mass of this object. So this is the formula of acceleration. So from this formula, if we want to calculate the magnitude of acceleration on any object, we need to find out the force, the net force which is acting on this object and the mass of that object. If these two things are known to us, we can easily find out the acceleration on that object. So to find out the acceleration, we need force and the mass of that object. So after learning all these things, let's learn a little bit about the gravitational force. The gravitational force is one of the four fundamental forces in the universe, and those fundamental forces are the weak nuclear force, the strong nuclear force, and also the electromagnetic force. And the fourth one is the gravitational force. So out of these four, I will be explaining only the gravitational force here. So the gravitational force is one among the four fundamental forces in the universe. The gravitational force is a universal force. It means that every massive particle in the universe will attract the every other massive particle. So if there are two masses, suppose there's a mass m1, this is the mass m1, and there's another mass m2. So between these two masses, there will be a force of attraction and we call it as the gravitational force. The magnitude of this gravitational force F, let's say F is the magnitude of the gravitational force. This is proportional to the product of the masses, that is m1 into m2, and this is also inversely proportional to the distance between these two objects. So if the distance is d, so that force of attraction is inversely proportional to the square of the distances. And if we combine, this gravitational force F will be equal to, because we are using equal here, so there would be a constant, we call it as the gravitational constant, into m1 m2 divided by the square of the distance, that is d square. This is the formula of gravitational force. The value of this capital G, that is the universal constant, is 6.67 into 10 raised to power minus 11 Newton meter square per kilogram square. This is the unit. So from the basic definition of gravitational force, that every massive particle in the universe will attract every other particle. So if there are two particles having certain mass, they will attract each other with a certain force, and the magnitude of that force is given by this formula. So now let's take the example of Earth. Suppose this is Earth and this is its center. The radius of Earth is capital R and the mass of this Earth is capital M. And let's consider there is an object which is at a height h from the surface of Earth, and the mass of this smaller object is small m, and this height from the surface is h. So this h is the height from the surface. Because these two bodies having mass small m and capital M, so there will be a force of attraction, and that force would be the gravitational force. And if we find out the gravitational force on this smaller object due to this bigger object, that is Earth, it will be given by this formula. So if I rewrite this formula for the force on this smaller object, this F would be equal to G into capital M, which is the mass of the Earth, into small m, which is the mass of the smaller object, and we need to divide it with the distance between these two. The distance between these two objects is r plus h, because r is the radius of the Earth and h is the height from the surface of Earth where this object is lying. So the total distance is r plus h square. So in place of d, I have to write r plus h square. So this is the force which is acting on this smaller object. And now if we want to calculate the acceleration of this particle due to its force, because we have just learned about the acceleration from the Newton's second law, if there is a force acting on any object, there will be an acceleration. Due to this force on this object, there will be an acceleration on this object. So we have to find out that acceleration. So that acceleration from this formula, the A, that is the acceleration, would be equal to the force, and the value of this force is capital G into capital M into small m divided by r plus h whole square. This is the value of force, and we have to divide this force from the mass of this object for which we are interested to find out the acceleration. So this whole divided by the mass of this object, that is small m. So from here we can calculate the value of acceleration which this object will go through due to the force of attraction by this Earth, or we can say that the gravitational force of attraction due to Earth, this will be equal to capital G, and from here this small m and small m gets cancelled. So the remaining equation will be capital G capital M divided by r plus h whole square. So this is the formula of acceleration. One thing is very interesting here is that because this acceleration is due to the gravitational force, so we have given it a special name and we call it acceleration due to gravity, and we have given it a special symbol as well, and that symbol is small g. Although these two are same, because this acceleration is due to a particular type of force, so we have given it a special name, that is acceleration due to gravity, and also given it a special symbol, that is small g. So this small g would be equal to this same formula, that is capital G into the capital M, which is the mass of the Earth, divided by r plus h whole square. This is the basic formula of acceleration due to gravity. So after learning about all these things, we will be finding out the value of small g, that is acceleration due to gravity, on the surface of the Earth, and we will represent it as g. We will also find the value of acceleration due to gravity at a certain height, and we will represent it as gh, and we will find out the value of g at a depth from the surface of Earth. So let's find out the value of acceleration due to gravity on the surface of Earth first. If the object is lying on the surface of Earth, the value of this h would be 0. So what all we need to do is to put the value of h as 0 in this equation. So this value will be the value of g on the surface of Earth. So I'm just rewriting this equation as g surface, or the value of g on the surface of Earth. This will be equal to the capital G, which is the universal constant, into capital M divided by R plus H is 0 here because the object is lying on the surface of Earth. So the value of H would be 0. So the only thing which is in the denominator would be R square. So this is the value of acceleration due to gravity on the surface of Earth. In this equation, we can see that the value of G is constant, which is constant everywhere. The value of capital M is the mass of Earth, which is also constant. And the value of R, which is the radius of the Earth, it is also constant. And if we put the value of these three constant in this equation, this will comes out to be 9.8 meter per second square. So the value of capital G on the surface of Earth is itself a constant, and the value is 9.8 meter per second square. But this value is valid only on the surface of Earth. The second is to find out the value of acceleration due to gravity at a height h. As we can see that this equation is representing the value of G at a height h itself. So all we need to do is to mark, we can write this G as GH because this is nothing but the acceleration due to gravity at a certain height h. And if I rewrite this equation here again, so this GH, that is the acceleration due to gravity at a height h, will be, all I'm doing is I'm just removing the constant terms here so that I can create a relation between the variable and the acceleration due to gravity. So the capital G is a universal constant, it is remains same everywhere, and the value of capital M is the mass of the Earth, which is also constant. So from here we can write that the acceleration due to gravity at a certain height is inversely proportional to R plus H square. Although this capital R is representing a constant term, but we cannot write it here separately because it is with the height h. And the value of h is a variable. It will keep changing as we move away from the surface. So from here it is clear that the acceleration due to gravity is a function of height. So this equation is representing the acceleration due to gravity at a certain height h. Now the third thing and the very important thing is that we need to find out the value of acceleration due to gravity at a depth d. To find out the value at a depth d, this involves two things. The first thing is the concept and the second thing is the calculation. So let's understand the concept part first. Suppose this object which earlier was lying on the surface of Earth, now somehow we managed to dig this Earth and this object is now lying here, which is inside the Earth, and it is at a depth x from the surface. So if this is surface, the depth is x. This x is a variable which is representing the depth. Now what will happen? Can I use h as minus x here? So the answer is no, we cannot use it here. There will be some other changes in this equation. When this object was lying on the surface of Earth, the whole mass of Earth, that is capital M, was contributing in the gravitational force. When this object was at a certain height h, then also this whole mass of Earth, that is capital M, was contributing in the gravitational force. But the case changes as we go inside the Earth. When we move inside the Earth, the whole mass of Earth, that is capital M, will not contribute in the gravitational force. Only a certain part of this mass will be contributing. So we need to find out that mass first. When this object is at a depth x, so we need to draw a fresh sphere. So suppose this is a sphere, and now what we need to do, we need to find out the mass of this new sphere. And let's assume that the mass of this smaller sphere, which is inside the Earth, is m nu. This is the m nu. So we need to find out the mass of this part of Earth only, because this is the part which is contributing in the gravitational force on this object. So we cannot take the value of mass m here, because as we move inside, this whole mass will not contribute in the gravitational force. So the only concept which is required here is to find out the new mass of the Earth, which is for the radius equal to r minus x, because the radius of this new sphere is r minus x. R is the whole radius, and we have gone x depth from the surface of Earth. So from here we can easily find out the value of radius of this new sphere. That is this is the new radius, and this new radius is r minus x. So we need to find out the mass of this new sphere first, and that mass we will be putting it here, and the distance between these two objects would be the r minus x. So from here, if we want to find out the value of acceleration due to gravity at a depth d, I will be writing it as at depth d, this will be equal to capital G, which is the universal constant, into, in place of this whole mass of m, okay, I am just using this equation, or we can use this equation as well. In place of writing the m or the capital M, I need to find out this mass, and this mass is m nu. So we have to find out this m nu, which is the calculation part. The concept is involved here is that we must understand that whole mass of Earth will not contribute, only certain part of that will contribute in the gravitational force. So in place of capital M, I am writing this m nu, which will obviously less than the capital M, divided by, in place of r plus h, that is the distance between the objects. So that here the distance between the objects is the r minus x, because r minus x is the radius of this smaller sphere. So that is the distance between these two objects. So in place of the distance, I have to write r minus x square. So this formula is very useful for us to find out the value of acceleration due to gravity as we move inside the Earth. Here the concept I have already explained. So the next thing which is left with us is to find out this m nu, or the mass of this smaller sphere inside the Earth. So to find out that mass, there is some certain assumption which we need to consider. The first assumption which I will be using here is, I'm considering here is that the density of Earth is uniform. So the uniform density, I'm just considering it uniform density. And let's say the density is represented by capital D. Capital D is the density. The uniform density means that the density for this whole Earth of radius r will be same as for the radius r minus x. So the formula of density is mass upon volume. This is the formula of density, mass upon volume. So what I will be doing, I will be using this formula to find out this new mass. If I talk about the whole Earth, the mass of whole Earth is capital M. I have assumed that the whole mass of Earth is capital M. So if I am just using this formula for the whole Earth of radius r, so in place of mass I will be writing the whole mass divided by the volume of whole Earth. Because the Earth is in a spherical shape, the formula of volume for a sphere is 4 by 3 pi into r cube, where r is the radius of the sphere. So this is for the whole Earth, and I am equating this with the density of this smaller sphere. So the mass of a smaller sphere is m nu, because I am assuming it to be m nu, divided by the volume of this smaller sphere would be 4 by 3 pi into r. R is the radius of a smaller sphere, which is equal to r minus x. So in place of r cube, I will be writing r minus x cube. So in this equation, 4 by 3 pi and 4 by 3 pi will get cancelled. And I can write m nu, or the mass of this smaller sphere inside the Earth, would be equal to this capital M, that is the mass of whole Earth, into r minus x whole cube divided by r cube. This is the calculation part. You need not to worry about it much, because the concept I have already told you. So this involves only the little bit of calculation. This equation is representing the mass of the sphere inside the Earth. So if we put the value of this m nu in this equation, this will give us the value of acceleration due to gravity at a depth d. So let's find out the value of acceleration due to gravity at depth d. So this is gd equal to capital G, which will remain constant everywhere. And in place of this m nu, I will be writing this equation, which is equal to the capital M into r minus x cube divided by r cube. This is the value of this m nu. Now further in the denominator, it is r minus x square. Now if we simplify it, we will be finding it that This will cancel out, and the value of acceleration due to gravity at a depth d would be equal to capital G into capital M divided by r cube into r minus x. And if in this equation I just remove the constant term, that is the capital G, which is a universal constant, capital M is representing the whole mass of Earth, r is representing the radius of Earth. If I remove these three items from this equation, so this acceleration due to gravity at a depth d would be directly proportional to r minus x. And always remember that this x is representing the depth from the surface of Earth. In this way, we managed to find the relationship of the variables with the acceleration due to gravity on the different locations. The first one was on the surface of Earth. The relationship was this, and the value of g, or the acceleration due to gravity, was constant. It was 9.8 meter per second square. At a depth d from the surface, it is proportional to the r minus x, and at a height h, the value is inversely proportional to the r plus h square. In the question, we are asked to find the variation in the acceleration due to gravity if we move from the center of Earth and move away from it. We have seen that when the object was lying on the surface of Earth, the whole mass of Earth, that was capital M, was contributing in the gravitational force. Not only that, when the object was at a height h, then also the whole mass was contributing in the gravitational force. But the scenario changes as we move inside the Earth. When the object was at a depth x from the surface of Earth, we have seen that the whole mass of Earth was not contributing in the gravitational force. Only the part of that we have drawn a new sphere. Only this part of Earth was contributing in the gravitational force. So it is obvious that as we move inside the Earth, the mass of the Earth, or the mass of the object which was contributing in the gravitational force, reduces. The radius of this new circle or new sphere was r minus x, because the radius of whole Earth we have assumed it to be r, and depth of this object from the surface was x. So from here we can see that as we keep going inside the Earth, the value of x will increase, and when this object reaches in the center of this Earth, the value of x will become equal to the r, because when this object is in the center, the depth from the surface will be equal to the radius of Earth. So the value of x will become r. So if the value of x is equal to the r at the center of the Earth, what will happen? And if we put the value of x as r in this equation, this term will become 0. So the value of acceleration due to gravity in the center of Earth would be 0. So till now it is clear that the value of acceleration due to gravity in the center of Earth is 0. On the surface it was 9.8, it was constant. So as we move from the center to the radius r, or from the center to the surface, the value of acceleration due to gravity will increase uniformly. So now if we draw the graph, suppose this is the graph. Here I am representing the value of g. Here I am representing the variation in the distance between these two objects, and this point is representing the center. So at the center of the Earth, the value of acceleration due to gravity was 0. And if this is the radius r, at the radius r the value is 9.8. So this value is 9.8. Here it is 9.8 meter per second square. And as we move from the center to the surface, the value increases uniformly, because this is the formula. Here the relation between the acceleration due to gravity and the variables are linear, so this will increase linearly. But the scenario changes as we move from the center at a height h, and that relation is given by this equation. So this was the relation which we have derived earlier. So here the relation is inversely as well as of the square. So this will be something like this. So this is the variation in the acceleration due to gravity from the center of Earth to the surface and as we move away from the surface to a certain height. So this is the graph, and if we match this graph with the options given, we can see that the option B is the correct one. So thank you for watching. If you have still any doubt, please let me know in the comment section. I will definitely try to figure it out. See you in the next video. Till then, take care. Bye bye.